continue to contract, right? And we talked about acetylcholinesterase, the enzyme that breaks down acetylcholine as the main way, not the main way, the only way basically by which we break down the signal. Today we're going to finish this part and we're going to talk about the physiology of the muscle as an organ. We focused so far on the muscle as a cell. We'll start to talk about how the muscle contracts as an organ. We'll talk about the muscle response. We'll talk about something that's called the twitch. And we'll talk about different twitches and so on and so forth. And we will see how much time we will have. The last part of the lectures and the slide that you have is going to be devoted to the energy resources. You already had your GRQ and assigned readings. So we will see how much we get into that. We'll probably not be able to finish all the slides you have in your PowerPoint slide right now. But basically, it's just a bit more in-depth discussion than what you have in the assigned readings. So worst case scenario, you'll still have your GRQs and assigned readings, and that of course will be for the exam. Okay? In exam next week, we'll send again emails, reminders about review sessions and such, but again, I will have my own review session the day before the class, before the exam. I think it's a 5, but I'm not 100% sure, and I don't actually remember where it is, so I'll just check. I think I sent you actually an announcement about that to an email on one of the first days of the semester about all my review sessions, but I will try to remember to send a reminder. Any questions before we continue? Anything about the exam? The exam, the same pattern. I had students asking me in which system are you going to ask more. Basically, what I'm doing when I'm writing an exam is I'm actually looking at the number of slides and lectures and try as much as possible to have the same weight that we gave in the lectures towards the exam. So you have more muscular-related questions because we had 3 lectures when we had 2 in endocrine and 2 in skeletal. Again, you have 3 voice threads and assigned readings, so just make sure you cover it all. But as you saw in the first exam, the major emphasis of the exam, especially the difficult higher order level questions, will be more about what we discussed here in the class. Questions? Okay, so let's complete. We already did this last time. I gave you this as kind of like an open, for those who did not submit it just as an open option to do after that. But the majority of you said, not this one, shoot. This is running so fast, right? This is the one, and this is what you say. My diet 1 control muscle contraction. So I'll deliver the next one later on. My due to muscle contraction, it's true. Okay, so who wants just to explain why we'll get, if we take a healthy person, why would we get more? Right, so that's the idea, wonderful. It's the idea that if we signal, we want to stop the signaling, right? And part of the stopping, or not part of, the major part is by breaking it down with acetylcholinesterase. So if you treat a healthy person, what you're changing is the balance. Now, even in the case of myasthenia gravis, the autoimmune disease that we discussed, when you provide a patient with a drug that basically will inhibit acetylcholinesterase, you need to carefully monitor that patient because you might change the balance too much, right? And you might have overcontraction. You don't want that. But if you have someone that doesn't have any problem with autoimmune disease and acetylcholine is just responding, what you'll get is over and over and over signaling and therefore overcontraction and no relaxation. Remember, the idea is that once the signaling took place and the calcium was released to the cytoplasm, then even if you have ATP, you don't have ATP, it doesn't matter. Basically, you will have all the time, the myosin heads will be able, at least, of course, assuming you have enough ATP. I should mention, you do need to have ATP, you'll still be able to bind to the actin filaments. Any question about this? Yes, Emma. Oops.
So with uncontrolled muscle contractions, almost like you're stuck. Would that?
Uncontrolled will kind of look like you're stuck, yes.
Okay, it's not like,
this is
like moving.
No, this is kind of like the rigor mortis that we discussed last time, right? This is basically overcontraction without being able to relax. You guys check your alerts. right now? Is that we're good? Okay. Yes, ma'am.
Is this related also to seizures?
Seizures typically are overactivity in the brain itself. Okay? Yes, Abby.
Would you have to work, like, would you have to compare the actual, like, continuous stimulation with the amount of calcium you have available? Because if you run out of calcium, what is the...
You will not run out of calcium, basically. You have so much calcium in the terminal cisternae that you're not going to run out of it as low, unless you really run out of it, but it's just going to be too problematic. Okay, so before we finish this, I do want to remind you of this part. And last time we had a discussion, I heard some students suggesting good ideas about this. In order to stop the contraction, then one of the things we need to stop secreting calcium, right? And we just said, how? We're going to stop sending action potentials, and we're going to remove acetylcholine. But we do have calcium ions in the cytoplasm, right? So what do we do about those? Where are they going to go to? Any ideas? Anyone wants to share? I know there were a few groups that I discussed last time that had the right answer for this. So again, the question is, what happens with the calcium inside? We'll start with Nicole first. Uptake, wonderful. Where to? Okay, so one, we're going to reuptake them back to the terminal cisternae. Great. How are we going to do this? That's the second question. Yeah. With a channel that will require ATP. Why do we need ATP for? Wonderful. Because we're going against the concentration gradient, right? We still, although we release calcium from the terminal cisternae to the cytoplasm, we still have a high concentration of calcium inside. So what's going to happen, we're going to push it back to the terminal cisternae, and for that we need an energy-driven pump. It's not the sodium-potassium pump, it's the calcium pump, but the same concept. So we're going to put energy into that. What did I just say? We're going to put energy into that reuptake. What does it mean? In other words, we need energy for relaxation, right? We already learned that we need energy for relaxation. In what manner, in what way? The ATP should bind to the actin filaments to release the myosin heads. This is the second reason why we need ATP for relaxation, because we need it to drive the calcium back. Otherwise, calcium will just stay there. Okay. So actively pump calcium back to the terminal cisternae. Okay. So now, from now, I want to shift everything that so far was at the level of the cell, of the muscle. Now let's think about muscle as an organ. Okay? And when we think about the muscle as an organ, I want to remind us that something we already learned, that all the myofibrils in one muscle cell contract together, right? And all the myofilaments in one, all the sarcomeres, everything in a given cell contract together simultaneously. But we do not need all the muscle cells in a given muscle organ to contract. I don't need all my 1,000 muscle fibers in my biceps to contract in order for me to flex my elbow, to flex my muscles. I just need some. So when we talk about an organ, it's a different level. The two main terms that we're going to use are tension, that we're very familiar with, and load. Muscle tension, the force exerted by a contracting muscle on an object. Basically, the force exerted by the pulling of actin filaments by the myosin heads. This will be translated to the connective tissues, tendon, and eventually to the bone. But we need to pull. The pulling is the pulling of actin filaments. The load is something we have not discussed specifically, and the load is the opposing force. It's the elephant in this diagram, right? And in order to really pull a bone, or to pull whatever the bone is trying to pull, the elephant, right? What do you have to have in this equation between those two terms? The tension has to be greater than the load. You can pull as much as you want. This guy can pull as much as he wants. You'll not be able to pull the elephant because the elephant is too big of a load. Okay, some basic terminology. right? Muscle contraction, we're talking about muscle shortening. Here it is, you can see the long muscle, and we're talking about the entire thing, not just the muscle, the fibers or the organ. And it's leading to muscle contraction, and basically leads to movement. We good? We agree on this? 1, 2, 3, yes, no, 1, 2, 3? Yes. Yes, wonderful. The answer, of course, is no. Now, it's not that it's completely no, but it means that it can be yes, and it can be no, it depends. So this is when we talk about isometric versus isotonic contraction. Isometric contraction is the case when your muscle contracts, but without changing the length of the muscle, or without creating movement. Basically, the bone will not move, and therefore the load will not move. Right? If you go, this is kind of like me in the gym typically, but not with so many of these green weights, right? But this is the way it looks. This person is trying to lift something, it doesn't work. There is no movement. That's isometric contraction. We can study isometric contraction in more details, in more physiological details, when just look at someone who is trying. So for example, we can take a skeletal muscle, right? Let's say it's the bicep, for example, and put it, anchor it in one side and then put a load, let's say 6 kilograms for this specific muscle. And then we can contract it. We can stimulate it and contract it. And the muscle will not pull. We can measure the tension exerted by this muscle, and we can look at the length, and this is what we'll see here. So first of all, there are two graphs here I just want to warn you. On the x-axis, we always have time in milliseconds, but then we have two graphs. The one at the top shows you the tension that is developed in kilograms, and that's the tension developed, again, myosin heads pulling actin filaments. At the bottom, what you see is the muscle length, and it's not in millimeters or centimeters or inches. It's the muscle length of percent of the resting length. So we're starting with 100%. That's the resting length. Are we going to make it shorter or not? The stimulus is right here, right? You generated action potential. And now what we see is we had an action potential, calcium ions were released, everything that we are so familiar with, right? And we'll start to have myosin heads binding to the actin filaments, and they will start pulling, so we will start to develop tension, tension, tension. The problem is that this specific muscle has a peak tension that it can develop. And in this case, it's about 5 point something, let's say 5.5. But the load is the elephant, right? The load is greater. So you don't have enough pulling forces to create a movement and to pull the load, the 6 kilograms, so you stay there until everything is relaxed. If you look at the length of the muscle doesn't change at all, right? Because you're trying, but it doesn't change. So if you look at your biceps, whenever you try to pull something really, really heavy, or any other muscle, the bicep is just the easiest thing to look at, right? You will actually feel the muscle, and you feel it's elongated at its resting state. So that's what we call isometric contraction. On the other hand, if I go back for a second to that wrong plane, this can happen, just not always happen, when we talk about isotonic contraction. So isotonic contraction is that you'll finally be able to lift, okay, or to pull. This is a lift example. This is the same muscle we had earlier on, but this time we changed the load. So now it's not an elephant, it's a small elephant, right? It's just 3 kilograms. So let's see what happens at the level of the graph. So again, we start with 100% length, and we start with zero tension. We stimulate the muscle. We have everything, calcium released, T-tubules, everything we discussed. Myosin heads start to bind, and we start to pull. What's the peak tension we can potentially generate in this muscle? Do you remember? About 5.5, right? It's the same muscle we had earlier on. So we can go beyond the 3, right? Once we cross the 3, that force exerted by the myosin heads on the actin filaments is going to be translated into movement, into kinetic energy. And the muscle is going to shorten, because you are right now shortening it, and you're going to pull the load. And everything is continuing the same until the muscle relaxes, and then the muscle will go back. This is isotonic contraction. Yes? it's resisting, you can think about the stretch, but basically it's resisting a load that is bigger than what you can pull. Okay? Okay. So, first question. Think together, talk a little bit with each other. Which type will provide more tension? Isometric or isotonic? A tiny bit more than 3, right? You had to overcome the load, right? So it's 3 point something something. And then we pulled. What was the max in the isometric? It was 5.5 or so, right? The issue is that with isometric, you are trying, you're putting your muscles, you're reaching the maximum potential peak tension that it can provide, just seconds ago. Okay? So you work, the muscle works as much as it can. It pulls as much as it can. Here you didn't need to reach the max potential, because once you cross the 3, halfway through the tension as it developed, you already translated the force to kinetic energy, to pulling the muscle. Isabel. If the weight of the mass would have been the same, the answer is yes, but then you won't. Okay, that's a great point. If you start at the beginning with isometric when it's still not translated, we'll come back to this later on, so don't worry about that. Okay, actually pretty shortly. At that point it will be just the same as the max that you can reach. Okay? You're going to squat in a short while, so don't worry about it. We'll do it. Yeah, it's a good point. Okay. And that's isometric. For those of you who Thomas, for example, right, who goes to the gym, but many of you go, anyone who is actually doing some exercise, right, will know that one of the best ways for you to work, to challenge your muscle would be to reach a failure point, right? Thomas, am I right? Okay, good. Right? You are lifting, you want to lift, but you actually do it in cycle, and at some point you just cannot do anymore. So you don't want just to do isometric, but it's important to work on the isometric because it gives you more challenge or more force. You make the muscle work harder. I want to go back to a question that is going to be a difficult question. If you're not getting the next question that the LC I earlier showed, don't worry about it too much, because actually it's a question that many science debated about this, and I'm going to show you what we think right now is the right thing. But for me, it's important for us to think just about the process. I want to go back to the sliding filaments theory. We know eyes and heads and so on. Let's try to think about isometric contraction, but don't think about the muscle as a big muscle. Let's dive into the sarcomere, okay, and go back to what we know about the muscle. I want you guys to try to do it by yourself, and after you do it, then talk with your peer. So I'm trying to address what happens at the level of the sarcomere, and I'm going to open this question now. I'm changing the numbers between the first round and the second round, but that's not the idea here. Where is it? Okay, I'm going to send it. So you can see there's the first thing that I want to emphasize, right, is that you chose between A and D, and that's the important part, right? Both of them make a lot of sense, basically, and it's hard to tell which one is true, and you can still find some debate between scientists, but I think we have strong enough of evidence now to suggest one of those. And let's go back. The correct answer, of course, would be D. Yes. What's going on? How can the muscle sarcomere shorten, but the muscle does not? So for this, hopefully I will not hurt any student here. We're going to use now the chair as the bone. Okay? Can we see that from the top? Can you see my rope as well? Okay, good. So hopefully not hurting anyone. I'm going to, the same thing, right, eyes and heads and everything, and actin filaments. I'm going to start pull the chair, okay? Am I putting now, pulling forces? Tension, right? Is that at this point isometric or isotonic? Isometric, right? There's no change in the muscle length, there's no change in the movement of the bone/chair, right? and I'm continuing, right? And then I'm pulling, and finally, we have a movement, right? Now it became isotonic, right? Now, what did I add to what we did last time with the students, me pulling the students? What is very evident here that we didn't have, or we had but didn't focus on? There was an elastic end to this, right? There was this rubber band. I don't know how you call this in English. I didn't know this. We call it in Hebrew, if you just don't say it, it's called underpants rubber. I'm not kidding you, because you used to use them for like making, but we just call it rubber band, whatever, right? But that's, sorry, again? Elastic, okay. So, perfect. Elastic components. Now, do we have an elastic component if this was the muscle organ? Do I have an elastic component? For example, the tendon, right? But it's not just the tendon. We have in all the epimysium, endomysium, perimysium, we have elastic components. Even inside the sarcomere, we have elastic components. So what happens basically is that the sarcomeres are going to shorten, but the muscle as an organ will not. And now, let's go back to the slide so we can see that in more detail. You're good, you're good. You survived. Okay, so we can use this more of like engineering model, if you will, for the biceps in this case, remembering the fact that we have the contractile components. We are very familiar with those, right? It's the myosin heads pulling the actin filaments, contracting. But we also have elastic components, okay? And it's not just the tendons. It's easiest to make the example and show and demonstrate on the tendons like I did right now with the rope, but remember that there are elastic components all the time. So if we take a careful look at the muscle contracting, and I'm back to what Isabel mentioned earlier, what happens if it's just a light load? In the beginning, it's kind of like isometric before we actually change it. That's exactly what we're going to see here. So here's the muscle as an organ. And the elastic components are represented here in the blue, right? So think about them as the elastic rubber we just used. Okay? And here is one sarcomere, another one, and another one. Okay, you can just see the actin filaments here. You don't see the myosin heads. When you start contracting, the sarcomeres will become shorter, and there is going to be more overlap. It's hard to see that, but they are becoming shorter. You can see the dashed lines here, how they change the angle. But most of the pulling is going to be translated to what? Look at the elastic filaments. To the stretching of these, just like we had right now with the chair, right? I pulled, if you looked at the elastic band, you would see that it's stretched. Only once we reach the maximum stretch of these elastic bands, and assuming we have enough forces, then these forces will eventually pull the load, if we can reach that point. Which means that even when we talk about I'm contracting my muscle and pulling a load, even then the beginning of the process is with isometric before it turns isotonic. There's a short part, right? It's kind of like the action potential. It starts with a local potential, and if it's strong enough, there's a threshold, it will become an action potential. Here, even isotonic contraction before it becomes isotonic will be with isometric contraction, because we're trying to pull, we're trying to pull, and we're trying to pull, more and more and more myosin heads will pull, and eventually we're able to pull the load. Yes?
So this elastic element, this isn't the same as actin, right? It's not like...
It's not actin. Actin is not elastic elements. So different ones found in the sarcomere. I mentioned that briefly when we talk about sarcomere. It's teething beyond anything else, but you do not need to know the names, right? It's different spring-like proteins that are part of the elasticity. Yes?
This isn't too obvious, but if you had an issue that you had just a small deficiency with proteins, would you have with that sarcomeres would have to contract a lot more than the
So if you have a problem with those elastic components, you'll need to pull harder, but you'll also have many other problems, because don't forget, those elastic components are also responsible for what? After we pull, what happens? The muscle needs to go back, right? That's elasticity. So we need those elastic components. We cannot play with them. Yes?
So do they run the entire length of the muscle?
So they will run the entire length of the muscle. They will run the outside of the muscle, connecting to the epimysium with the tendon, those connective tissues. So that's the difference between a muscle as an organ and the basic sarcomere. It's a difficult concept. Okay? So just to summarize, isometric contraction, muscle's length does not change during muscle contraction, no movement takes place. Isotonic contraction, muscle length changes during muscle contraction, movement takes place. I'm just rushing because we talked about it a lot. Okay? So isotonic contraction, again, muscle length changes during muscle contraction, movement takes place. Okay? So we change, just to make sure we got this at least right. Muscle length changes, muscle shortens, right? Again, I will not call Thomas all the way here, right? Even my pull biceps, as I contract, they will become shorter. We agree on this one at least? Yes, no, 1, 2, 3? Yes. Yes, you should have known at this point that it's wrong. If I'm throwing you something that is so obvious, it's probably tricky here. The answer is not no. The answer is it can be yes and it can be no. So the muscle can contract and shorten, but the muscle can contract and lengthen it. What's up? How is that possible? This is when we distinguish between two types of isotonic, concentric and eccentric. When the muscle shortens, and what was your first kind of like default thought, this is what we call concentric isotonic contraction. But we can have an eccentric isotonic contraction. This is when the muscle lengthens. So how does it make sense, right? Let's make some sense out of it. All of you, take your right hand, okay, and put it on your arm like this, forearm, and your left forearm, okay? Now, before you do that, let's just practice. Let's pump our muscle just once. Flex our muscle right here and relax. Now, use your hand just to feel your biceps, okay? You can feel it. And when you contract, it became rounder and shorter. You feel that? That's what we call isotonic, right? And that's isotonic, what, concentric or eccentric? Concentric, because that's the easy part, the default, right? Let's challenge our muscles. Let's put your arm, okay? So we extend our arm, and we will use the right hand now as an opposing force. So try now to contract the biceps, but tell your hand, your right hand, to be stronger. So I'm trying to contract, but I'm not allowing it, right? There's an opposition here, a resistance. Now, does my biceps contract at this point? Do I have myosin heads binding to actin filaments and pull? I do, I feel it, right? Is there any movement? No. What is this? What type of contraction? Isometric, wonderful. Now, let's start to have more myosin heads binding to more actin filaments and continue to pull. We're still with the resistance, but now we're going to win over the resistance. This is not isotonic or isometric? Isotonic. What type of isotonic? Concentric, right? My biceps became shorter, rounder. We still have the same muscle, so just rounder. Okay, now let's continue with the same. We're starting with this position. Go back to the flexing position. Now I'm going to use the right hand to push, okay, so I can extend the arm. So first of all, I just do one easy round. Let's push it. Great. Now let's go back. Now I'm going to push, but my arm, my left arm is going to resist, okay? So no movement here, right? Isometric. Now we are pulling. We are pushing. Now my biceps, make your biceps resist it. Does your biceps contract right now? Yes, it does, right? Myosin head pull. Otherwise, it will just go like this. What happens to your muscle? It just lengthened. Okay? If you think about you go to the library, you pick up your anatomy physiology book, right? And you did not carefully plan, and you realize, oh, it's pretty thick, right? And before you know it, it's almost dropped to the right, drop down, and definitely do not want it to fall on the floor. It's your anatomy physiology textbook, right? So you hold it. Now imagine this was a really, really thick book, right? You'll try to make sure that it doesn't fall, and you'll contract, but if it's really heavy, and it's not just a book, but something really heavy, your muscle will be pulled because of the gravity and the load. Okay? If you think back about the guy who's trying to pull the elephant, he'll try to pull the elephant, but the elephant will be stronger, so not only he will not be able to do that, but the elephant will start pulling. That's eccentric contraction. On the slide, you'll have a YouTube that shows you the example we just did and many others. You're welcome to use it. And Isabel, did you mention who mentioned the squat? Right? This is a perfect example of basically all of these together. Right? So when we do squat, just one of many potential exercises you can do, but maybe the one that if you had just to do one, that's it. That would be probably work on more muscles than anything else, right? What we work mainly on different muscles, but we focus here on the quadriceps, right here. These are the main workers here. And what you do is that you're going to do all the isometric, isotonic, eccentric, concentric, etc., etc. In this case, the eccentric is going to be once you bend, okay, and the gravity itself pulls your muscle, pulls your butt, right? You are about to fall on the floor, but you don't. Why? Because the quadriceps are contracting and holding you. But if you stay like this, especially if you have a load, they're going to extend, extend, extend until you put enough force in pulling them up. Okay? What are you sitting for? Come on. Everyone who is physically capable of, please stand. Let's do some squatting and think about the forces.